Hello everyone, and thank you very much for joining me today. It will be a short lesson today. We discuss a simple algorithm called the Sieve of Eratosthenes. Always struggling with that word, and it's a nice to know algorithm. It's a student-like algorithm. A nice to know because even if it's simple, it's quite used within cryptographic algorithms in general. And I'm just going to share my screen. I don't want to spend a lot of your time. It will be just a very short one, as short as the algorithm is. The purpose of this algorithm being finding out the prime numbers up to a given number. So how do you find out prime numbers up to a given number? As I was telling you, the interesting what makes this the algorithm interesting is the fact that it's actually used throughout real cryptographic algorithms, and security is one of my hobbies. So that's why I decided to put it here. Not that I do expect you will actually write this algorithm quite a lot, but I know that you are curious about finding out as much as possible about things or pieces of the things that are used throughout the other capabilities that you call in your application. So as I was telling you, what we want to do is to find out with this algorithm the prime numbers up to a given number. So look, this is how the sieve of Eratosthenes works. You basically start by considering all the numbers to the given one you want to find out as being primes. So how do you do that? Simply by using an array of booleans, and we can call it primes or whatever you want to call it, so it's irrelevant. Of course, choosing the name is always relevant, but for the current given situation, I will just call it primes. I hope that's enough for our understanding. So the 1000 here means that I would like to check all the numbers up to 999. 1000 actually is 999 because it's actually the last index, no? And in an array starting from 0, the last index will always be n minus 1. That's why this n, which will be up to the number we are looking, is actually the primes length minus 1, because if you don't cut out that one, you will end up with an array index out of bounds exception in Java, no? So what I'm starting with is I'm going through the entire array, and I'm making sure that all of them are true, because if you leave it like that, it's all of them are false. Well, you can use the switch, like consider the false being prime and the true being non-prime. That's possible as well, but hey, it's a little bit nasty, no? I mean, it's strange to do that, so I prefer to have it. Even when I use this is a tip for clean coding and stuff. When I use a boolean, I want to be suggestive, including its values, not only its name. So it's strange to say true for a switch that's off. No, it's the other way around, so it should be false, because otherwise someone going through your code and trying to read it will find it difficult, I promise you. So I'm doing this. I'm going through the entire array first and make sure that I do consider everything prime. So starting with them, I do say, hey, you are primes, and then I try to find out which is actually not prime, and I'm trying to go through all the numbers. And we all always know that what is a prime number. Maybe I should have started with what a prime number is. I did consider this elementary enough, but a prime number is a number that divides only by one and by itself, so it has no other divisors between 1 and its own value. 2, 3, 5, 7 are examples of prime numbers, and if you've studied math enough, you know that they are more and more apart. So the more you search, the more apart they are. And it's also not proven that they are either finite or infinite. So it's believed that the set of prime numbers is an infinite one, but as far as I know, this wasn't proved by anyone yet. Okay, I hope I'm not wrong. This is only my general culture. I'm not a mathematician, but that's as far as I know from my readings. So what I'm gonna do now, I'm gonna start with the second, and I do start with the second because 2 is actually the first prime number, so we don't actually care about 0 and 1, so they will not be used out of our array. 2 is the first prime number, and with it we start to clear out which are the numbers that are not prime. And then what I'm gonna do is I'm gonna use a condition that might look a little bit strange at the very beginning, but you will see later when we finish the algorithm that this is actually to cut out a large part of the iterations that you would be doing. No, because normally I could have started from I directly. No, so I don't mind starting from I, but if I do start from I, then you will have a ton more iterations than they are necessary, because you will see that mathematically speaking, you don't need those iterations. So this I squared is actually the value squared that you are searching for non-prime numbers at the beginning, and it's basically it's proven that theoretically all the other that would have been previous to this value would have been already found out through iterations of the smaller numbers. So if you don't understand what I mean now, no worries, because you will understand it at the very end, and I'm gonna do some debugging as well. So then I'm gonna say I plus plus, and then I will say, hey, if this is prime, so if I reached out a prime number, then I make sure that all the other numbers that are multiplications of the current one are marked as being not prime. Why? Because if it's a multiplication of the current number, it automatically doesn't have only one in itself as a divisor. So that actually means that it's enough. So I must be smaller than square root. No, because what I'm doing here, so you are making a confusion with finding out what a prime number is, but that's not what I'm doing here. You will see I'm doing something else here. I'm iterating through the entire array. So the purpose of this for is not to iterate to find out who's dividing something. I'm iterating through the array of indexes. This is not the algorithm for finding out if a number is prime. The sieve of Eratosthenes, it's an algorithm that finds out all the prime numbers up to a given one, okay? Starting by the fact that we know 2 is a prime number. So bear with me here, you will understand better. So no, it's not square root here, so that would not work, because n really has to be the last index of my array, meaning the last possible number that might be a prime number, okay? So that's why this is not a square root of n here. It would not work with a square root of n here. So I'm going and I'm saying if I found the prime number, and being that I start with 2, it will be true, because remember, in the very beginning all of them are true. They will become false afterwards. So I'm going then with another iteration, say j from I times I, okay, smaller than the last number, and including the last number, which would be 999 in my case. Of course, we know it's not a prime number, but our algorithm needs to work regardless of your input here. So remember, this one should actually be your variable of input. So if it's not clear enough, I can actually say something like input is 1000, okay, and then whatever the input is, you put here, okay, just so this is the input, this is the number up to which you look for primes, okay. So I'm going from the square of the one that I have. Why the square of the one? Because all the others would have been already found out, and then I say up to the last one, and then I do add itself. So I'm going to all the multiples of the number that I have been, and then all of this, it's clear they are not primes. So I'm just gonna say it's not prime, and that's it. This is the whole algorithm. So I promised you it's a short one. We will parse through the entire array now, and we will first of all validate that it works correctly, so I don't say any, I don't know, garbage here, because I don't want to teach you garbage. And then I'm gonna go through the entire one, because I know that if it's the first time you see this algorithm, it might not be straightforward for you, but I promise you it's not that difficult once you get the idea, and we will also take it manually and see it. So let me do the following. I'm going through the entire array starting with 2. Why 2? Because I know, and it was the presumption of the whole algorithm, that 2 is actually a prime number, and up to the last one, which is n. And then I'm gonna I'm gonna say if primes of I, if the number is prime, print it out. So I is the number. So remember, basically from this, the indexes represents the numbers we are checking. The value in the array is whether they are or not primes. So true means it's a prime number, false means it's not a prime number. You start by assuming that all of them are primes, and then you eliminate of them. So that's basically what the word sieve means. No, I'm not sure how to say it in another way, but it's eliminating those that are not prime. On the presumption of the definition of a prime, meaning a prime number cannot divide with anything else than itself and 1. So that actually means that anything that's a divisor of a prime number will automatically be non-prime. So, and then you can see here that I'm starting from the beginning to see that it's only prime numbers that remain here: 2, 3, 5, 7, 11, 13, 17, and so on and so forth. All of these are the prime numbers, because what we did was to eliminate the non-primes. So now what happens is that you have these numbers. No, it's 2. Oh, let's put them in a comment. Oh, sorry. Let's put them in a comment, like 2, 3, 4, 5. I'm starting with 2 because, again, the 0 and 1 are irrelevant here. And 6 and 7, 8, and I'm not gonna put them all, of course, because it's irrelevant and we will stay here too much. But now start assuming we are starting, so all of them are primes. No, that's what we've been starting with, that all of them are primes, but we know that's not true. So we are starting with 2, and another thing that these algorithms presume is that 2 is a prime number, and we know that, of course, we know 2 is a prime number, and we know it's the first prime number. So it's not only that 2 is a prime number, but also is that it's the first prime number, because this algorithm doesn't work if you don't start with the first prime number. So that means that means I'm entering this for the first time for 2, and then I'm taking for 2 times 2, which is 4, up to the last one. So I'm starting with 4. You see, I'm starting with 4, and then I'm adding 2 every time. So automatically this one disappears, this one disappears, this one disappears, and you see, this way, basically taking them this way, all of them will disappear in the end, so it goes up to the end. And then you do it finishes, so you do the following: you automatically go with the next one, which will be 3. So you go with 3, which is this one, and then automatically you start with 3 times 3. Observe that 3 times 3 is also the first non-prime number, because all the others have been eliminated by prior iterations. So you do the following with starting from 9. 9 plus 3, of course it happened to also be a divisor of 2 12, so you don't have it anymore, and then plus 3 15. Okay, and then it would be 14, but it's no longer here because to eliminate it, 15 automatically is eliminated. So, and then you do this with all the next prime numbers. So 4 will not be taken anymore into consideration because of this condition. It goes into 5, 5 remains in place, and then automatically it will take out all the others starting with 25. So 25, 30, 35, 40, 45, 50, and so on and so forth. So whatever you want, it basically starts with the first prime number and eliminates progressively all the others that have divisors, the prime numbers, because you will always end up only with primes, and everything else would have been automatically considered non-prime. So this is basically how it works. I see some questions. Is a log of n which is quite fast? Well, yeah, I'm not actually sure, because you do have here an if indeed, but you do have one more iteration inside. I think you are right, however, but it's basically, as far as I know, the fastest in which you can obtain this. However, remember that even if it's a fast complexity from the processing time, it's a larger one from the space time, because you need to keep all the values in this array. So it's an O of n in terms of space complexity. And then understanding is that I'm not sure if that's a question or not, but yes, this one is basically used especially because prime numbers are used in cryptographic algorithms. You will find it within security algorithms in general. So if you want now, as last concern, we can go through the entire algorithm, and I want to make sure step by step that you understood. Of course, I have already tried to manually run the algorithm here on the set of numbers, but you might want to see it also running. So let's see how it works. So I'm gonna go step by step, and I'm gonna skip, of course, because I don't want to step over the whole parsing through the array 1000 numbers. So you know now, and please look here, that everything changed into true, meaning we do consider all the values being prime. And remember, then the first two are not interesting because they are representing values 0 and value 1, which we know they are not prime. So but we start from 2. I don't know a better way to do this, so I'm just starting usually from the second index representing the second number. And then you say starting from 2 here, okay, is 2 a prime? Yes, because we anyway started by considering everything be prime. And then you say, okay, now start from its square and then add everything that's after, make them non-prime. So look what happens here, starting with 0, 1, 2, 3, 4. This one is the first one that will change into false. No, so bam, it changed into false. Now this was representing a number 4. Maybe it's better if we see them like this, no, because you see also, so 4 became non-prime, and then if you go a little bit further, 6 will be the one next, 8, then 10, then 12, because now it's adding 2. So every 2 values, they become non-prime because they are now we observe they divide with 2. So being that they divide with 2, it makes no sense for them to be considered prime. It's clearly they are not prime anymore. And then I'm gonna just go to this again, and this, when it reaches the if again, it is because it finished parsing the entire array, and it continues with the next value here, which is 3. So see, now I has the value 3, you can see it here, and it repeats the same thing starting with 3. So 3 times 3 will be 9. Okay, please do observe that before that all of them that are non-prime have been already excluded. So now it goes to 9 and makes 9 false, and then 12, but it was already false from the 2, and then 15 becomes false as the next one, and so on and so forth. And when it finishes, it continues to the next number, which will be the next one that respects this condition will be 5, and then will be 7, and so on and so forth. Always the next one fulfilling this condition will be the next prime number, because all the others have been eliminated previously by the previous iterations. So this is, my friends, how this simple algorithm for finding out the prime number up to a given one works. And remember, a nice to have, it's a student-like algorithm. It's not something I expect you will have to implement at some point in your career, but it's always interesting to know what's behind the scenes of everything, and that's how your brain becomes more algorithmical. You gain some algorithmical thinking, you improve your skills in algorithmical thinking, and so on and so forth. Sorry for that. With that, I'm waving goodbye. I hope you like this short video, and until next time we meet, I wish you an excellent time for learning further. Cheers, everyone.